Hello everyone, welcome to my Your Programming Club. Today we will be solving another daily LeetCode problem, and the problem's name is find the city with the smallest number of neighbors at a threshold distance. So you will be given n cities, and those will be numbered from 0 to n minus 1, and there will be an edges array given to you. Each entry in this edges array will represent connection between two cities, and the weight or the distance between those two cities which are connected by this edge. Okay, so from city from a certain city to a certain city, and this is the distance that it will take to reach uh, from source to destination, you can say, in a way, and represents a bidirectional way and weighted edge between cities, two cities. Okay, so the edge will be bidirectional, you can go both ways from city 1 to 2 or 2 to 1. Okay, and given the you will also be given an integer which is the distance threshold. So the distance between two cities should be not be greater than this threshold. Okay, you have to return the city which is connected with the smallest number of cities. Okay, or you can say smallest number of cities are reachable from this city via some path, and whose distance is at most the threshold distance. Okay, there are two things. The first thing is that let's take the board and write it down. The first thing is that the city should have minimum connections. City should have minimum cities or minimum connections. Okay, so it means that the number of cities that are reachable by this city should be minimum. The second condition is that the all the number of cities that are reachable by this city should be within the threshold distance. Okay, and these minimums that we are counting should be within the threshold distance. Okay, these are the conditions that we have to check for all the connected cities to a certain city. Okay, and if there are multiple such cities which are having the least number of connections and within the threshold, both of these conditions should be satisfied in order to consider a city to be connected to one city. Okay, so the threshold limit should be there, and if there are such cities which are having same number of limit connections, and all those connections are within the threshold, then in that case the city having the larger number will be returned. Okay, so if let's say 3 was connected to 4 cities which were within this threshold distance, and 5 was also connected with 4 cities which among which all these 4 cities they were within threshold distance from 5. So what will be the answer right now? So these two are having same number of connected cities within the threshold distance. In that case our answer will be the greater numbered city. Okay, it will be 5. So this is what it is saying here, and you have to notice that the distance of the path connecting two cities I and j is equal to the sum of the edges weights along that path. Okay, so for example, if let's say we are going from 1 to 2 and there are some intermediate cities coming in between. Okay, and and they are also having some distances to them. So our total distance from 1 to 2 will be the sum of these distances. Okay, 2 plus 1 plus 3, which is equal to 6. So 1 to 2 you will be taking 6 distance to reach. Okay, so this is what the problem statement is saying here. Now before thinking of an approach, let's quickly have a look at the constraints also. So according to the constraints, the number of cities will be of order 100, and the edges will be of order n square basically. Okay, and edges length, each entry in this edges array will be of size 3, and it is mentioned that all the cities, whether it's the source city or the destination city in the edges array, will be ranging from 0 to n minus 1. Okay, and the weight and the threshold distance that will be given to us will be of order 10 raised to power 4, and all pairs are distinct between the source and the destination cities. So there are no self loops. It will not happen like tree is having a path to itself. Okay, so this kind of situation will not exist. Okay, pardon please. This kind of situation uh, can exist basically, but here it's mentioned that although if a city is connected to itself, it is having zero distance because we are already at that city. So this it is quite understandable. And the last constraints is saying that there will be no duplicate connections. For example, 3 to 4 you are having one connection, then again 3 to 4 you are having another connection. So this kind of situation will not be there. These pairs will be always be distinct. Okay, so that's the problem statement meaning by this particular constraints. So let's try to think how we can solve this particular problem. So what we can do here is we can apply Floyd-Warshall algorithm here. So Floyd-Warshall algorithm can be applied. Those of you who are hearing this uh, algorithm's name for the very first time, or are not familiar with this algorithm, although I will be explaining this algorithm in this video itself, but if you are more curious about it still after watching this video, then you can find a link to the Floyd-Warshall algorithms article in the description of this video. So now let's discuss what happens in the Floyd-Warshall algorithm. So let's say we have to find the shortest distance between A and B. Okay, between two cities A and B, we have to find the shortest distance of the path. Okay, and let's say it is right now some x value. Okay, so right now they are connected directly with it, which is with each other. Okay, and so let's consider a scenario in which A and B are connected with the intermediate node. Okay, so this is A, then there is some intermediate node, let's say it is C. Okay, and then this C is then connected to B. Okay, and let's say instead of X, let's take some numerical value. Let's say this value would have been 5, and these two values were 1 and 2. So you can see that there are two paths to reach right now from A to B. So you can consider the situation like this. Okay, so this was taking 5, and it was taking in a total of 3 distance. So you can see that the second path, or the this path I am talking about, is more favorable because it's taking less distance. So we can consider this intermediate node to be included in the path from A to B instead of going directly. Okay, so this is the whole idea of this Floyd-Warshall algorithm. What we will be doing is, let me write it clearly here. We will consider each node to be an intermediate node, or possible intermediate node, and yeah, possible intermediate node, or you can say intermediate node. I think it was fine to be an intermediate node which might reduce the distance between two cities. Okay, so this is what we will do in the fluid Warshall algorithm for for each node or each city. We will consider the possibility of it being a intermediate node between two cities. Okay, and we will consider all the paths that are going through this city and leading to two different cities in a way that this particular city is a intermediate node. So what I am saying is, let's say this is C. C might be a connecting node to different pair of cities. Okay, for example, it was connecting A and B. Then there was some other pair it was also connecting. Let's say it was connecting D and E also. Okay, so there can be different cities it can be connecting. Okay, let's say there was some another pair it was connecting. So let's say it was connecting G and F also. Okay, so as you can see, there are number of paths that might be going through C, and C might be acting as an intermediate node for n number of pairs of cities. Okay, not exactly equal to the number of vertices to be necessary, but you can see that C can act as an intermediate city for many pair of cities. Okay, so we will consider this kind of possibility. Let me change the color here. This kind of possibility for a city to be an intermediate city between all the pairs possible between two cities, source and destination, and we will optimize our distance array. So what kind of distance array we are talking about, or the distance graph? Let's take a new slide. So we will be having a 2D array. So it will be the source and this will be the destination. So you can call it a distance graph. Okay, it will be a 2D graph, and let's consider there were two cities, source city and destination city. Okay, we have to check the distance between these two, and we will update this distance if this represents the distance between source and the destination city. Okay, this distance graph value. Okay, and we will update this distance if there is an intermediate node which is helping us to reach from source to destination in a less distance. So if distance graph, if the distance of source from to the intermediate, okay, let's call this inter, plus distance of, of intermediate to the destination, okay, is lesser than the distance of source to destination, it means the direct edge. Okay, this is the direct edge from source to destination. Okay, let's change the color here. Okay, if rather than taking the direct edge, as if we take some intermediate city and it is helping us to reach in shorter distance, so we will update this distance between the source and destination. Okay, so that will be the crux of this particular algorithm, and let's have a quick look at the implementation so that you will be able to understand it in a more clearer way. Okay, so let's take the code to the board and let's start with a flash slide. So this is the code. I know it's a little bit lengthier code, but be patient and we will be able to understand all this, what is happening inside this particular implementation. So let's reduce the space consumed a little bit so that larger portion can be visible. Let's remove the toolbar also. Okay, I hope right now this entire code is visible to you, but let's say let's zoom in this much. We can scroll it definitely. So let's see what's happening inside this particular code. So as we talked about, we will be needing a graph. This graph will represent the distance it will take from reaching one city to another city. Okay, by two dimensions. One dimension is for the source city, and another one will be the destination city's dimension. Okay, and initially we will fill all the entries in the graph with infinite values. So a value large enough so that the distance some cannot reach, or the path some cannot reach to that particular value. And from seeing the constraints, we are able to see that maximum integer value will be that a value, it will be the sufficient value to be taken as infinity. Okay, so once we have done that, then for the city to itself, its distance will be 0. Okay, so distance of city to itself will be 0. So let's take the marker here. So distance of city to itself is 0. Then after doing that, you will take into account the edges array that is given to you and update the distances of the connections, direct connections that are present between two cities. Okay, and since it was mentioned that the edges are the bidirectional edges, so you need to do both way, from A to B and B to A. Okay, that's why we are doing it two times, from once from 0th edge to the first edge, and first to the 0th. Okay, and this will be the weight, because this was the structure of the edges array, as you can see here also. Source in a way, and destination in a way, and then their distance or the weight. Okay, so once we are done with it, then we will start considering each city as the intermediate city. Okay, start considering each city as intermediate, and we will update the distances of all the possible pairs which can achieve a shorter distance between them by passing through this intermediate city. Okay, so what we are doing here, updating distances between all possible pairs which can achieve less distance by going through the intermediate node. City or node, whatever you may want to call it. Okay, so then we will be considering the pairs of the cities. So the first city and the second city. Okay, and although a city is connected to itself in a way, so but we will be avoiding that kind of situation. And what we will be doing here is, if first of all, the very necessary condition is that if you are considering from A to B, and you are considering to take one intermediate from A to C and then C to B, okay, then in that situation this particular edge should be feasible. All these three edges should be feasible, otherwise you cannot consider them. Okay, although these are not directed edges, please keep in mind, so this should be feasible. Okay, so this edges should be possible, otherwise we will not consider such a scenario. So that's what we are doing here. We are checking, let me change the color here. whether these edges exist or not. Okay, from first city to the intermediate city. Okay, this particular edge, this edge we are talking about. Let's change color here. From the first city to the intermediate city, and then similarly from intermediate city to the second city, and this should be existing. Okay, otherwise it will be difficult for us. So if these conditions are satisfied and we are good to go, then we will check for the possible updations. Okay, if we are able to achieve the lesser distance, for example in this case, if this kind of situation is existing, we will be checking for this kind of situation. Okay, otherwise the distance will remain same between the first and the second city. Okay, so this is what is happening in this particular section. And once you are done with all these things, you will be having a direct distance graph, which will be storing the shortest possible distance between a pair of cities. Okay, so once you are having that, our job of finding the answer city becomes really easy. We will just loop through this particular 2D array, and for each source city we will be considering all the possible destination cities and seeing what is the city's reach, or the how many cities we can reach from this source city within the threshold limit. Okay, and we will increase our city's reach with each such city that we find, destination city. And then we will update our minimum reach, which is by the way initialized to a maximum value that in or an infinite value. Right now it represents infinity in a way, and you will keep updating it, and as per that our answer city will also be keep updating. And for the condition, this condition that when two cities are having same number of connected cities within the threshold, we should be considering the greater one. This will be automatically taken care of when we will be going from 0 to n. Okay, because we will be going from the lower number to the higher number. Okay, and because of this equality uh, check also, we will be for sure storing the larger city as our answer city in that kind of scenario. Okay, and there is a then we will be returning our answer city, and there is a thing that you must keep in mind, that this particular intermediate city loop should not be the innermost loop, because it will result in the late updations of uh, some city distances, pair of city distances, and those late updations will result in the wrong answers. Okay, you can try to have a dry run of it by taking it as a inner loop and then taking it as a outer loop. You will understand what I mean by late updations. Okay, so that is all. And if we talk about the complexities, complex time complexity wise, if there are n cities given to you, because of use of this particular loop, as you are seeing it is a nested loop, so overall time complexity will be order of n cube. Okay, and space complexity wise, since we are using a 2D array of n square size, so our space complexity will be that much. Okay, so space complexity wise it will be order of n square. Okay, so this is the overall approach. And if you are still having any kind of doubts or any queries in general, then you may ask them in the comment section. I really hope this solution walkthrough added some value to your journey of honing your DSA skills, and keep solving more and more problem, and I will see you in the next video. Thank you for watching.